In the next statements, we will use these estimates of the remainder terms, starting with a very simple limit that I want to state. Simple but important. The limit of x going to 0 of sinus of x divided by x. Of course, here both is going to 0, so we don't know what's coming out. And it turns out that this is indeed 1, which is a nice thing because actually this says that they behave similarly close to 0, because we really get 1 here. So yeah, you can say this like sinus x is behaving similar to x when you are very close to 1. So this is kind of the interpretation of this result. So how to prove this? I will now take the notation from the previous remainder estimates and say that we get that the sine of x divided by x. So we've seen the first summand in this power series representation of sinus was just x, and then minus, and for the rest we already take a remainder, so let's call this R3 of x. So this is something which starts with x to the 3 over 3 factorial, blah, 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 so just higher powers. And we divide this by x, and this of course is the same as 1 plus R3 of x divided by x for all x in R without 0. Yeah, okay. So this is something we can write first. We can write this down, and now if we are close enough to 0, we get an estimate for R3. And since we just want to study the limit for x going to 0, this is enough for our purposes here to compute the limit. Namely, we get now by Theorem 379. No, sorry, 380, sorry. Yeah, by this remainder estimates, so we get, if we now use this computation, we take sine x divided by x minus 1. And so we want to show that kind of this goes to 0 as x goes to 0. First of all, we know that, of course, this is a non-negative number, which is obvious. So we have sine x over x, and now we use this representation, and then we see that, so this one and this one cancel each other out, so we get R3 of x divided by the absolute value of R3 of x divided by the absolute value of x. And now we get that we have this estimate here, and this estimate said that this is smaller than the absolute value of x to the power of 3 divided by 6. And so here we get another copy of the absolute value of x. And now, of course, this can cancel out here the two copies of the absolute value. And so we get x to the absolute value squared divided by 6. And this, so if the absolute value of x is smaller than 4. So, yeah, and x not equal to 0, of course, otherwise this doesn't make sense. So we see this is smaller than or equal to 0. This here goes to 0, so by our inequalities for limits, this then implies that we get that kind of the sandwich argument. This is caught in between 0 and something that goes to 0. And so we can conclude that this really, this is theorem, yeah, first of all, so here we need that the limit of x going to 0 of x squared divided by 6 is 0. And so now by this inequalities between the limits, this was theorem 360. So if we have an inequality between the functions, we get one between the limits. This implies that the limit of x going to 0 of sine x divided by x minus 1 is 0. This, of course, means that if the absolute value is going to 0, that the thing inside is going to 0 without the absolute values. And this, of course, means that the limit of x going to 0 of sine x, this should be an implication here, sine x divided by x is 1, which we wanted to show. So here we just use that sine x is x plus something small, and this is small enough not to disturb our computation here. This is the idea behind this. Okay, yeah. So next thing, we want to study sine and cosine a bit further. So we have seen some nice properties, but we still haven't studied the function, like how they behave as functions themselves. So we haven't thought about the graphs and so on. So this is what we want to kind of go to the next. So first of all, we want to, kind of collect some properties of the behavior of sine and cosine. Which values does it take? How does it behave? And the first thing that's very easy is that the cosine of 0 is 1. The sine of 0 is 0. B, the sine of x is positive for all x between 0 and 2, so the open interval 0 and 2, okay. So this interval could be bigger, but this is something we want to prove first. So you remember from high school that the zeros of sine were always the powers of pi. So this is related to the number pi. But so far we have a problem. We don't have pi yet. We haven't defined the number pi so far. But we will do this kind of using the properties here, and we will do this in terms of the cosine in a bit. So this will be a bit awkward, but this is kind of the way that you can define pi rigorously in our framework. Okay, so on this interval 0, 2, the sign is positive, and now we want to study the cosine on this interval, and you can see that the cosine, if we restrict the cosine to the closed interval from 0 to 2, there it turns out that the cosine is strictly monotonically decreasing. And there exists a unique, x0 in the interval from 0 to 2 in the open interval with cosine of x0 is equal to 0. So there's a precisely one value where cosine becomes 0. Okay, so let's prove these properties. The first one is basically trivial. Namely, so we have the real part and the imaginary part of e to the I times 0. This is, of course, e to the 0, and this we've checked to be 1. And the real part of this is 1, the imaginary part is 0, done. Okay, part B. So here we again use some smart estimate, namely the same as we used just in a proof of the previous corollary. By theorem 380, we have that the sine of x is x plus r3 of x, and we have that the absolute value of r3 of x is smaller than or equal to the absolute value of x to the power of 3 divided by 6 for all x in minus 4 in this interval. Okay, sorry for squeezing again. So this is what we have. Now this will be used. So we know that this is kind of with the values we have this upper bound. So in particular we know that this means that r3 of x itself has to be bounded from below by minus x to the power of 3 over 6 if x is positive. So then this would be, of course, so yeah, we would derive this from this inequality, that this cannot be below this because otherwise the absolute value would become too big. So this holds for all x in 0 to 4. We have to be a bit careful with the sign if we would have negative numbers, of course, but anyway. So using this, we get that if x is between 0 and 2, then we can make a nice estimate. Namely, here we know that, so this was the estimate here. So if we combine this with the previous inequality, this inequality with the previous display here, it shows that if x is so small, we get that sine x is bigger than or equal to x minus x to the 3 over 6. So this is the same as x times 1 minus x squared over 6. Now, if x is between 0 and 2, yeah, how bad can this be? Yeah, no, sorry. Sorry, the mistake, sorry. This here, this negative number. So how bad can this be? This can be, x is not bigger than 2, which means that this is not, x squared is not bigger than 4. And so in total, we get that this is bigger than or equal to x of 1 minus 4 over 6, so which is 2/3, which means that this is x over 3. And this is bigger than 0 for all x between 0 and 2, of course. So this shows the first part of the claim. So the part B of the claim here. Okay, so the sign is positive there. And now part C requires a bit more work, so we need to show this monotonicity of the cosine. So we want, let us first check directly the monotonicity. So we take two elements of the interval from 0 to 2, which we want to investigate, and we assume that one is smaller than the other. So let's say x is smaller than y. So now we need to show the inequality between the cosine of x and the cosine of y, the opposite inequality, since it's decreasing. So for that, we introduce some new variables, basically, or some new quantities. I define u to be x plus y divided by 2, and v I define as y minus x divided by 2. Okay, then we have a nice property, namely then x, if we just compare these two, x is the same as u minus v, and y is the same as u plus v. Okay, yeah, that's true, but why is this interesting? This is now really helpful as it turns out, namely now we can make a clever estimate. So if we take cos x minus cos y. So to show that this is strictly monotonically decreasing, we need to show that this difference here is just some positive number. This is now in terms of u's and v's. This is cos of u minus v minus cos of u plus v. Now, these are additions, so we can use these angle sum identities. So this is by the angle sum identities, or the one identity of them for cosine. This says that this here is cos u times cosine of minus v minus sine of u sine of minus v. And the second summand here, this is then minus cosine of u cosine of v, and now we get a minus minus plus sine of u sine of v. Okay, now we can use the symmetry properties that we had, and we've seen that the cosine is doesn't depend on the sine, and the sine of something of minus something, we can pull the minus out there. So this was theorem 377. So just the symmetry properties. This means we get cos u cos v minus sine, plus, if we pull this out, plus sine of u times sine of v, and the rest stays as it is. Cos u cos v plus sine u sine v, and here we, of course, we see that this guy and this guy, they cancel each other out, and it doesn't remain that much more, so this is the same as 2 sine u sine v, which is by definition 2 sine of x plus y over 2 times sine of y minus x over 2. And now there's it's easy to see because x and y are in this interval, and because this inequality holds that this here is bigger than 0, and you can also see that this is bounded from above by 2, so this is in 0, 2. And here you can also see this is also in 0, 2. So by part B, this is positive, so the whole thing is positive. So this is just part B, which we have just shown. So we've proven cosine of x is bigger than cosine of y, and so we've shown that the cosine is strictly monotonically decreasing on this interval 0, 2. Okay, now, so we've seen it is strictly monotonically decreasing, and we want now this to find this property of this 0. So first of all, since it's strictly monotonic, we get that thus the cosine restricted to 0, 2 is in particular injective. We've seen that strictly monotonic functions are injective. And we know that the cosine of 0 is 1. Cosine of 0 is 1. And I claim now that it suffices to get the claim, to show that the cosine of 2 is negative. Why is this enough? I would now ask the audience if I had one. So we have a positive and a negative value, and we have a continuous function, so it's now again the intermediate value theorem. So then the intermediate value theorem shows the claim. So this shows that there is such a point at which the function becomes 0, and the injectivity here shows that it's unique. So all that remains to show is this. Okay, So how do we do this? We again make a nice estimate because we again use theorem 380. By theorem 380, we've seen that cosine of x is, and now we expand three summands here. The first one was x squared over 2. The next one is x to the power, only two summands, sorry, this is enough, plus some remainder term, where this remainder term satisfies R4 of x to the absolute value is smaller than or equal. Sorry for the cut, I made a tiny mistake. The estimate for the remainder is this one. We get that the fourth remainder here is bounded from above by the absolute value of x to the power of 4 divided by 24, which is 4 factorial. So here we had 4 factorial by the previous theorem for all x in here. So this means, hence, for all x between 0 and 2, the cosine of x is smaller than or equal to 1 minus x squared over 2 plus x to the 4 over 24. And now we just need to insert x equal to 2, and now I've run out of space, so I do this after erasing. If we now insert 2 into this latest formula, we get that the cosine of 2 is smaller than or equal to 1 minus, and now we have 2 squared over 2, which is 4 over 2, which is minus 2. And we get plus 2 to the 4, which is 16, divided by 24. So this is 1 minus 2 is minus 1. This is 2/3. This is minus 1/3 in the end, and which is, of course, a negative number. And so this shows the claim, as we've said before, with this intermediate value argument. And so we get that there's a unique point in 0, 2 at which cosine becomes 0. Okay, now this leads us to this next definition, and this is probably the most awkward definition of the whole lecture for you. Because we define the number pi, and I'm now mutilating another Greek letter, sorry about that, pi in R. Pi is defined as 2 times this 0, this point at which the function becomes 0 that we've just obtained, namely twice the minimum of positive numbers x, such that the cosine is 0. Okay, this is now a really, really awkward definition of pi at first sight. So if we recall from high school, so how is pi actually kind of defined, or how it's historically defined, and so on. Given any circle in R2, so pi is defined as a ratio, which is always the same for every circle, namely the ratio of the circumference divided by the diameter of the circle. So this is actually how it should be defined, how it sounds reasonable. But this is now within our axiomatic framework actually really the same number. This is quite awkward, and it was kind of, basically in high school you did it the other way around. You showed that this is kind of the same number for every circle. Then you derive it there at some point where the cosine is vanishing or something, but yeah. Anyway, so we do it like this. So we define pi like this, and now derive nice properties of pi in the following. So this is our definition here. Okay. Sorry, I just made a stupid mistake, so I had to cut again at this point. This now helps us in computing some values of the exponential function. And let me make a quick drawing here on the side. So remember we had e to the ix was part of this, was always lying on this unit circle. So here we have 1, here we have I, so the whole thing is c, 0, here we have minus I, and here we have minus 1. Okay, so we know, we've seen, the interpretation was that we have always the point e to the ix is the point at which this angle here is x. So this would be e to the ix. Now, using pi, we get some nice results for using this definition of pi. We can compute e to the I times some values related to pi. The first thing would be e to the I times pi over 2. This is equal to I. So this would be here, this would be a 90-degree angle in this drawing, and this makes sense with before because we know that 90 degrees, so a right angle, as a radian, it's pi over 2. This is how we kind of learned it in high school. So e to the I pi is -1. So this is over here, this would be a 180-degree angle. So yeah, then, and also kind of as a radian, this would be pi, as you know from school, so this kind of makes sense. So this would be the first one, this would be the next one, and then now you can probably guess what's coming next. E to the I times 3 over 2 pi, this is minus I, and finally e to the I times 2 pi is 1. So 2 pi describes a full circle, so a 360-degree angle here in this setting. Okay, now we have defined sine and cosine as the real and imaginary parts of this e to the I something. So we get some values of sine and cosine as well. Let me just make a quick table here. So sine x, cosine x. So if x is 0, we've seen that sine is 0, cosine is 1. Now if pi over 2, there we see that this is I, so the real part is 0, the imaginary part is 1. So at pi, we get -1, so the real part is -1, the imaginary part is 0. Here it's minus I, so here the imaginary part is -1, and the real part is 0. And finally, 2 pi, we have again real part 1, imaginary part 0. Okay, and then we get this periodicity that we don't have yet, but that we shall see in a bit. But first of all, we have to compute these values. Okay, how to do this? Actually, it's not too complicated. So, first of all, by definition of pi, so by construction, the cosine of pi over 2 is 0. This is the way we defined it. So we get that the sine squared of pi over 2, we know that sine squared plus cosine squared is 1. So this is 1 minus cosine squared of pi over 2. And this is 0, so this is 1. So we know that the sine of pi over 2 is either 1 or -1. But we've already seen that, so by construction, pi over 2 is smaller than 2. And we've seen that on the open interval from 0 to 2, the sign is positive. So it can only be 1 by Theorem 382b. So real part 1, real part 0, imaginary part 1. So this implies that e to the I pi over 2 is exactly I. Okay, so the remaining parts, they are now again basically derived from our miracle equation. Namely, e to the I pi, this is the same as e to pi over 2 squared. Simply by this miracle equation, since this would be pi over 2 plus pi over 2. So this is this term squared, and so by what we just shown, this is I squared, and this is -1. And now the rest goes like this as well. So e to the I times 3 over 2 pi. This is e to the I pi times e to the I pi over 2, again by this miracle equation. So this is -1, this is I, this is minus I. And finally, e to the I times 2 pi is e to the I pi squared. So again by equation e. And so this means we have -1 squared, which is 1. And we already have it. So it's that easy actually. So we already have determined these values here. Okay, in particular, let me formulate this as a remark, because this is something that is a bit outstanding, I would say. Namely, one of the things we've shown in this computation is the so-called Euler's identity. That's the following one. We've seen that e to the I pi is -1, which can be a bit reordered to say that e to the I pi plus 1 equal to 0. This is an amazingly beautiful equation. In fact, in the 90s at some point, this was voted by readers of the magazine The Mathematical Intelligencer as the most beautiful equation in mathematics. And I've read this many times that this should be kind of considered to be probably the most beautiful. So why is this so beautiful? Think about it. What do we have all in this equation? We have the 5 most important constants in all of mathematics. 0, 1, I, the imaginary unit, pi, and e. So the Euler number. All these constants in one nice, concise formula. Also, we've got all elementary stuff combined. Then we got the most important operations in mathematics. We've got plus, addition, we have time, multiplication, that's here, and we have the exponential map, which kind of controls all powers. And so kind of all important operations in this nice little concise formula with all relevant constants that you kind of need to do mathematics. It's kind of an amazingly beautiful formula which kind of, it feels like it's some higher truth or something in there, but we just can't recognize. But this is just beautiful. Okay, I just wanted to mention this because it's something that you should at least kind of see this once. Okay, Theorem 386. Now we want to come to the properties of sine and cosine regarding periodicity and so on. Namely, that x in R, then, first of all, and this is something I'm quite sure you know already, sine and cosine are 2 pi periodic, meaning the cosine of x plus 2 pi is the cosine of x, and the sine of x plus 2 pi is the sine of x. So it's always repeating itself. This, after a length of 2 pi, we get the same thing again. Okay, part B. The cosine of x plus pi is minus the cosine of x, and the sine of x plus pi is minus the sine of x. Finally, both are closely related, sine and cosine, as the following shows. The cosine of x is the sine of pi over 2 minus x, and the sine of x is the cosine of pi over 2 minus x. So they are indeed very similar. Okay, how do we see this? This is, again, just computing with exponential function and using the values we just obtained. So, proof. So, to get this periodicity results, we basically only need the exponential map of e to the I times this arguments of these functions. So, we get that e to the I times x plus 2 pi. So here, real and imaginary part are the sine and the cosine here. So by our, first of all, this is e to the ix plus I times 2 pi. And so by our miracle equation, this is e to the ix times e to the I times 2 pi. And we've just seen that this is 1. So this is e to the ix. And so if we just take the real and the imaginary part, we just get this equation. These equations. It's that simple. So just direct, straightforward computation. Okay, so take real and imaginary parts. Okay, for b we do a similar thing. So for b we have x plus pi. So what do we have in this situation? We take e to the I times x plus pi, which is the same as e to the ix plus I pi. So by our favorite equation, this is the same as e to the ix times e to the I pi. And there we've seen that this here is minus 1. So we get minus e to the ix. And here we of course get the real part of an imaginary part of this here, of course minus the real and the imaginary part of e to the ix, which are minus cosine of x and minus the sine of x. And so we get the claim. So again, take real and imaginary parts. Okay, for C, it's maybe slightly more work. C, here we get this equation. So this is what we want to show. So we want to take pi over 2 minus x as the argument. So let's do this again with the exponential map. E to the I times pi over 2 minus x. Again, we can multiply. This is e to the I times pi over 2 minus ix. So miracle equation. This is e to the I pi over 2 times e to the minus ix. And we've seen that this is I. So this is I to the times e to the power of ix. Okay. Now let's write down real and imaginary parts of this. Then it becomes minus x. Sorry. Let's write down real and imaginary parts of this. Then it will probably become a bit better. So here we get the cosine of pi over 2 minus x plus I times the sine of pi over 2 minus x. So here we get I times, and now the cosine of minus x plus I times the sine of minus x. And here we've seen the symmetry properties of sine and cosine. So cosine of minus x is just cosine of x. And here we just can put the minus in front. So this is minus I times sine over x. And now we just have to multiply, and I'm running out of space. So I times minus I here is equal to 1. So we get sine x plus I times cosine of x. And if we now check sine, the real and imaginary parts, these are precisely these two equations. So we're done. Okay, this shows the periodicity. Let me erase.